as I mentioned to you, we give the word to Lea for presentation. And you already see on the screen that she's presenting. So, Lea, just try to stay into less than 10 minutes, if it's possible. And then we have our discussion. Okay, so I take my glasses and my phone. Good. I think you can even remove this if you click on, but I mean, it's not a problem. Yeah, but you see it here. I think you should click here. Sorry. Okay, here. It should disappear. Yes. Yeah. Okay. Okay. When you are ready, you can start. Okay. Let me just make sure that you have the micro that is, because I don't think, should be connected mine. Just let me check, because you are connected with Teams. Okay. Yeah, but not with the microphone. Okay, I think it should work. Yeah, it works. The other one, yeah. Yeah. Yeah, please don't be Yeah, okay, so for those who don't know me, I'm Lea Weitenberger. I'm currently doing my Erasmus in Bologna. And yeah, I'm here for half a year and also, yeah, doing this course. And I would like to present you my bachelor's thesis topic. And it was mainly about sustainability in bridge construction, because I also worked in a bridge engineering office and it was related to the office. And yeah, but I'm not allowed to say that much about it because all the rights are reserved by the company. But I just wanted to show you a little what I did, and yeah. So first, no. Yeah, no. Okay, first I would like to show you the problem we have with bridge abutments. So I don't know if you had any lectures in bridge construction here. Yeah, so you should know that one. Okay, just to be sure. And maybe you know the problem that we have massive dimensions, especially when it comes to the bridge abutment, and also massive cross sections. And I have another plan over here where you can see that even though the wall are 2 meters, it's a lot. And for example, when you're thinking about all the concrete in these abutments and the CO2 emissions out of these concrete productions, it's a lot. And that was mainly the problem I was thinking about. And so I wanted to show you the CO2 emissions of concrete production. Maybe you know a little bit about that. Maybe not. Maybe yes. So the problem is the cement, or especially the clicker. And it's not a massive, like it said in the headline. It's only 10% of the concrete by mass, but it's 90% of the carbon footprint. So nearly 90% of the CO2 emissions out of the concrete productions are because of the cement production or the clinker production. And yeah, then I don't know if these are the same in Italy as in Germany, to be honest, but these like the concrete classes. And yeah, so yeah, I'm German, so people like referring to Germany, but yeah. Yeah, so the CO2 emissions can be decreased by 10% if you're just going down one class. So maybe when you're building bridges in the future, maybe think about it, just not using a special class only because you're using it, but maybe think about, do you really need it or not? Then finally, my topic of the thesis. It was the optimization of time and resources for bridge abutments, and therefore I focused on modular constructions, but mainly with like prefabricated, but not completely prefabricated. It's only half of. And as I already told you, the massive dimensions and especially the long construction times lead to high material and energy consumption, which is no longer like appropriate with the view of the climate crisis. And yeah, I think we all know about that. And then I also focus on the influence of traffic on CO2 emissions, because maybe you don't know that, but huge part of the CO2 emissions when we're building bridges or maintaining bridges is because of the traffic that is like the like what do they call it? Like more traffic you have when you maintain a bridge or build a bridge, and maybe the cars had to take a longer way to work or whatever, and therefore I focused on the influence of traffic on CO2 emissions, and it was huge, just to let you know. And then, as I told you, I focused on the modular construction method and compared it with the traditional monolithic construction, and analyzed the potential for faster and more resource efficient construction processes. So I focused on time, costs, and materials. But yeah, I'm unfortunately not allowed to talk about that. Maybe I can talk to you in person after the lesson, but here I'm not allowed. So what I wanted to show you is the influence on the CO2 emissions. I know it's in German, but yeah, I think you can see it. So the green line is the influence on the CO2 emissions, and you can see that especially in the initial phases, you are able to have a huge impact on the CO2 emission. But after that, it's just decreasing, because when the materials are set and the dimensions are set, you're not making a huge difference in CO2 emissions anymore. So think about it before. And it's the same with the costs. Maybe you know that one from a project management class or cost analysis or whatever. It's a McLeamy curve. Yeah, it's the same with the costs. So when you're focusing on the cost before, you can reduce the cost. And in Germany, we have a shadow price for CO2 emissions that is coming in a few months, maybe. And then you have to pay for every kilogram or ton you're producing in emissions. And therefore, maybe you need to think about the influence of the CO2 emissions to also think about your costs in the end. Yeah. And now that is also a topic of my bachelor's thesis, was CO2 optimized construction methods and building materials. First, I have high strength concrete, Sonocrete. It's a German company, which is relatively new and a startup. Recycling concrete, prefabricated constructions, carbon reinforcement, and basalt reinforcement. And just like 2 sentences to each, and that's it. So for high strength concrete, a pro is that you can make like delicate cross sections, because you need less concrete because it has a high strength. So the CO2 emissions are higher, but you also need less concrete. So in some bridges or dimensions, maybe it will be more sustainable than using a normal concrete. And the con is that we don't have regulations in Germany. I don't know how it's about Italy, but in Germany we don't have. And yeah, this bridge is the Marseille in France. Maybe you know that one. It's the entrance to a museum, and it's 115 meters. Then we come to Sonocrete. I don't think that you ever heard about it. So first, it's pro. It's low. You need less cement because you're mixing water and cement in a bypass system, and then you treat it with ultrasound. and therefore it builds bubbles and they're expanding, and yeah, so this like so then they come to an unstable phase and then they're bursting at a specific size, and that promotes the formation of C and H phases, which makes the concrete even, yeah, which hardens the concrete. And yeah, so you need less cement for the same strength of concrete, which leads to less CO2 emission. And the con is that there's little construction experience because it's a startup. But yeah, they were really nice. I talked to them, and yeah, they're really nice. Then recycling concrete, I think most of the people heard about it. So I can be short about that one. The pro is the reuse of demolition materials, so you don't need to use new materials, you can reuse. And the con is that you have a reduced frost and de-icing salt resistance. Yeah, which yeah leads that you are not able to use it in every case. Then to the prefabricated constructions, the pro is the shorter construction time, as I already told you, and the elimination of formwork work, because you can use like this prefabricated and then just fill in the other concrete, for example, also recycling concrete or sonocrete, or you can use like completely prefabricated materials or construction, and then you just don't need to do anything anymore. Maybe some small parts where you need to yeah.
Can you please say again the question if it was a question?
No, I wasn't not sure. Maybe I just go on. Okay. And you also need less reinforcement, because when you're using prefabricated constructions, they are mostly made out of high strength concrete or nearly high strength concrete, so you don't need to care about the cracks that you in the early age of your concrete after you put the concrete there. So you don't need to think about that, and that is mainly the point why we need that much reinforcement in bridges. But yeah, maybe that's a bit too deep into it. And I don't know. And the cons is that you have a higher planning effort in the initial phases of the project. But yeah, yeah, maybe think about it in the beginning and then you have a better outcome in the end.
Differences on non-verification and non-verification. So when you see the email market ad, you can match it up then. That really get to get one.
Turn on the mic off. Thank you.
Do you have a question or?
I don't know who is talking. I think it's Rada. Did you have a question, or it was a mistake that you were talking with the micro open?
Practice
Because I can't really hear what you say. Sorry. Can you please repeat?
It was a mistake.
It was a mistake. Okay. Thank you. Yeah, move on.
Yeah, and then the second last point is carbon reinforcement. Maybe you heard about that one. The pros to very high tensile strength, and the con is that we only have a guideline since 2024. At this point, I don't know about Italy, but yeah. So compared to steel, you need less, and you also don't need 5 centimeters of concrete cover because it's resistant to corrosion. Yeah. And at least the basalt reinforcement, I think, basically is the same as the carbon reinforcement. It's stronger than steel and also resistant to corrosion. And it's volcanic natural stone, so you have very low emissions. But the corners, you have a limited offer, and especially in Germany, it's hard to get it because the ways are long, and therefore you just have other CO2 emissions because you need to bring it to Germany. Yeah, and I think in Italy there are I think it's mainly.
There are many places where there are basaltic rocks, and because it's soil, I don't have a clear picture, but anyway,
Okay.
I know the cost.
Okay. And yeah, the summary is that the use of semi-fabricated components leads to a significant reduction in construction time and environmental impact, and meets the challenges of infrastructure and requirements of the climate crisis. Because yeah, in Germany we have a lot of problems with our infrastructure, and we have a lot of bridges that needs to maintain. And innovative approaches offer great potential for reducing CO2 emissions. So maybe think about it, and that's it.
Okay, and yeah, I make a comment and then I ask you a question. And if you have other questions, first of all, I think the topic is very relevant, and it is very relevant because you know that in the case of the climate crisis, as you said, it's one possible solution is reduction of the pollution. And this is part of the mitigation process. Mitigation means that we try to remove climate change, and under the assumption that climate change is mainly caused by human emissions. If you reduce human emissions, we reduce climate change. This is one solution. Keep in mind that it's a solution in the long term because it takes a lot of time for the climate change. And some people say that it takes more time to recover than the time that you do get. So it's a solution that should be integrated with other solutions that are part of adaptation. Adaptation means that in the presence of climate change, we try to mitigate the impact. And there is the problem of resources because we don't have resources for everything. And the big question today is the priority adaptation rather than mitigation. But on the other hand, it's clear that any effort that we may make for reducing the carbon footprint of humanity is possible. And therefore, the topic of construction, sustainable construction materials, it's really becoming very popular and international level because we need a lot of CO2 emissions that come from construction. Okay, just to give you a couple of suggestions, when you give a given time, I can explain.
Yeah.
You have 10 companies. I can say how much, how long was your extra time, but there was some extra time. So try to, especially if you have an interview.
Yeah.
I have some interviews where they say you have 3 minutes to present yourself. It must be 3 minutes ratio. So try to get a compromise, and the solution is trying to years. Second thing, the tone of your voice is important. If you get an interview, try to be excited. Excited by the interview, try to be enthusiastic. Really, the people, the companies look for motivated people, so enthusiastic. Your presentation was a bit more calm. And just the topic is very interesting. It could be also to something getting going for a master degree. You are not taking your master degree here, but just what I would like to know that, of course, it becomes more practical. It is really relevant. So I think if you are passionate about it, you have the potential for exploring more. My question, I didn't understand the influence in traffic during the construction or traffic during the normal exercise.
During the construction, but also when you maintain a bridge, because when the bridge is closed or you have like traffic, then you have a lot of cars standing there waiting to get over the bridge or whatever, or maybe they need to take a longer way, and therefore they're like producing a lot of emissions. And so the influence of the traffic was 2 times as high as the CO2 emissions of concrete.
Really, 2 times.
Yeah, I did a comparison, and in the end, I think it was nearly 2 times as high. So it was a lot, yeah.
But of course, there is some traffic that you would have anyway, so.
Yeah.
But I understand your point. And this is documented, there are studies documenting that the traffic.
Yeah.
Do you have any other question?
I have a question regarding the construction method that you use in Germany, which is the most used and useful.
The traditional monolithic one, so that you're just like having the formwork, and then just putting the concrete in there. But no, like usually we don't use prefabricated or semi-prefabricated methods in Germany for bridges. But when it comes to houses or something similar, then we use semi-prefabricated components. So it depends, but in bridge construction, no. I don't know about Italy, but yeah.
I would see that, I think, I can simply reply that it's the same situation with your master constructions. And I don't have the answer to other questions that you made, like the regulations. And I don't know if the reinforced concrete is regulated or not. I don't think so. This is something that you should ask to my colleagues working in structural mechanics. Can you please go back to the first slide with the graph? Where blue line yeah, this one. So I didn't understand. The German doesn't help. So you are in the horizontal axis. What is the horizontal axis?
This time, so it's like the beginning of the construction.
Okay.
This is the influence or the possibility of influence.
Influence of what?
Influence on the CO2 emissions.
Okay. This is the green line.
No, this is the green line.
Green line.
And the red line is the potential of less CO2 emissions. And the blue one is the time and the effort you need for making changes. So it's getting higher quality and then you're not able to change anything anymore. Because in the beginning, the time and the effort for changes is not that high, and therefore you are able to have a difference of CO2 emissions.
Okay, yes.
Yeah.
And so in the long term, your effort needed to make changes is higher.
Yeah.
Effort means the cost.
No, it's more when the initial project phases, for example, when we are deciding which materials we are using, it's easy to say, okay, now we're using a more sustainable material, but in the end, when everything is already built, you're not able to say, okay, yeah. Yeah.
Okay, that's fine. And the next one is basically, I don't know how many carbon, so it's effort and time.
Yeah.
I used to live with.
But actually, I found that one there in English.
Yeah, but the cost of design changes. So, design, Basically,
Yeah.
now it's clear. Do you have any other question?
Yes, sir.
Yeah.
About the sonography,
Yeah.
we say you use the less cement
Mhm.
rather than the normal concrete.
Yeah.
But for increasing the strength of concrete, you use some additive in your mixture design, like microcities, nanocities, fly ash, or not.
No, I don't think so. You are able to use them when you need them, for example, but no, they're just using this ultrasound bypass system, and because of that, you have a higher strength. So it's not like combined with
This
additional.
technology makes the strength.
Yeah. So the ultrasound, yeah. Like because they are treating with the ultrasound, I think I don't have the picture in here. But you mix water and cement, and then you treat it with ultrasound, and then there are bubbles, and they're expanding and floating, and then at some point they are unstable, and then they burst, and then when you then mix it with all the other components, you can you have a higher strength because it's called it's better for the CSH phases. So it's easier for them to develop CSH phases, and because of that, it hardens the concrete, and because of that, it has a higher compression strength. Yeah, yeah. But I can also give you like the web page of Sonocrete. Maybe that's easier because they have like a whole diagram how it works. Yeah.
Okay, any other question?
Okay.
Okay, good. Thank you. Thank you also for coming in presence because it's much better.
Yeah.
Okay, so you already moved this, perfect. So the adapter and
How long I was supposed for?
I told you less than 10 minutes and I think you got to some 12 because net was 14, but there were 2 interruptions. So I think you had 2-3 minutes more than. But I mean, I'm not strict. I just made the comment because I think your presentation was really good because it was pertinent and understandable. And I just made a comment for your, I mean, for giving a suggestion, you know. But the presentation was fine. For level of career development, is okay. How long were you? Did you present for the thesis, for defending the thesis? Okay. Okay, I see. I see. Okay. Okay, good. So let me share the screen. But before sharing the screen, I think I can put the camera on the blackboard because we don't need screen sharing now. I just want to stay on the blackboard for a while. Okay, so now let me go back to probability because in order to move forward with the slides of the American Society of Civil Engineering, in order to define the level of the extreme, the relative period, the issue of stationarity, we need to complete our introduction to probability. And let me check the symbol. Actually, I want to check on my webpage the symbols that I used, because if possible, I try to use the same symbols here at the blackboard. Firefox. So now. This is the box on probability. I'm going to see the box on probability that I showed to you before. I'm not sharing the screen now. Okay, I am using F for the frequency. Okay, good. So let me share the screen. Anyway, I think it is better if I share it. Okay, here is the screen shared and okay. Good. And then I pin the blackboard. So you should see the blackboard big remotely and the screen small. Okay. So what I did earlier was for tossing the dice. Actually, I could have waited before deleting it. 3, 4, 5, 6. What I did before was to show in the graph the probability for each outcome from the dice, and the probability is 1/6. 1/6. Here is x. X is my random variable, okay, and here is p. Px. And then what I also did was to cumulate it in order to build the cumulative probability. Okay, so let me just try to respect the scale more or less. Something like this. Okay, and this is the cumulative probability. Okay, not very precise, but it's a straight line. And basically, you can see from here that the probability is the difference. So the cumulative probability is the sum of the probabilities. The probabilities are the difference of the cumulative. Now, let's refer to a similar graph for a continuous variable x again. And here we put px. Yeah. Okay. Or let's say, let's put px. Yeah, this is fine. Now, the problem with the continuous variable that I generated before, which was in the interval between 0 and 1, is that if I fix a value, for instance, of 0.5, and if I want to estimate the probability by counting the outcomes that are equal to 0.5, it's 0. Okay, so let's suppose now that we really want to solve this problem. And let me generalize it with 0.1, 0.2, 0.3, 0.4, and then 0.6, 7, 8, 9, 1. Okay, for each 0.1 fraction from 0 and 1, I want to estimate the probability. And how can I do that? So let's focus on 0.5. So if I want to count the number of outcomes that are equal to 0.5, they are 0. So what is a solution that we could think of? The solution is, for instance, focusing to discretize the variable, the random variable, focusing over an integer. So I could say, let me look at here. And this is the interval between 0.4 and 0.6. So this is 0.5. So my delta x is 0.1. Now, if I refer to an interval, I can count the number of outcomes that are inside the interval. And this allows me to compute a frequency. Okay. So, for instance, let me indicate the frequency with f. I can count the number and call it as a capital F frequency of x plus minus delta x, and then x plus delta x, and this is equal to, let's suppose that the total number n is the sample size, so the total size of the numbers that I generated. So let's suppose I generate like 1,000 numbers. So n is 1,000, okay? So the total number of data. Now the frequency can be computed by counting n in the interval x minus delta x, x plus delta x, divided by n. Okay, so let me put a star here. I'm not sure if in the lecture I have the same number, just to make a difference. So what I'm doing is I refer to the interval between 0.4 and 0.6. I compute the number of n star of data that are within this interval, and I divide by n. Okay, and this is something that approximates the probability of 1.5. Okay, so this is a possible solution. If I want to estimate the probability of 1.5, I look to an interval around 1.5 and I compute the frequency of the data inside it. Is this clear? Okay. And one could see, okay, it's not. And then I can make a graph. On the other hand, you may say, yes, but if you do like this, there is a problem. The problem is that your probability of 0.5 is driven by the size of the interval, which is not acceptable. I mean, the probability of 0.5 shouldn't be driven by the size of the interval because it becomes subjective. So if I say 0.5 is a short probability, a small probability, it must be small irrespective of the size of the interval. And therefore, the idea is to divide the frequency by the size of the interval. Okay, so the probability, which is indicated there with an F, lowercase, let me indicate it for clarity as E of x is equal to the frequency of x minus delta x, x plus delta x, divided by 2 delta x. Okay, so I take the frequency that I estimated and I divide it by the length of the interval. This is the definition of probability for a continuous variable. Of course, this is the way to compute it based on data. This is reasonable. Let's try to do it over Excel. Okay, so now I unpin the camera. And then the screen is shared. Let me start an Excel file. Okay, and let me, okay, I think the size is fine. Let's make it with 15 numbers, random numbers, okay? Let's create our data. And so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, okay? And what are the random numbers? Now, let's generate the number with a different generator. Before I did, in the morning, I did it with casual or randgen. Now, let's make it with, I think the function is norm, but let me check, okay? It's not norm, maybe it's normale. Not valid, just 1 second, let me check over
Google. So Excel generation normal distribution. Generating number of numbers, and let's see, it's no, it's this is random, but it's normiv. Okay, normiv. Okay, now let me. It's in English. You should use this one. Normiv rand. In Italian, let me check. Excel. Generazione. Distribuzione normale. Should be something like inv norm n. Okay. Should be distrib norm n. Inv norm n per trovare il valore. Okay, inv norm n. Let me try. Should be not normale, but inv norm. Okay, inv norm n. Sorry, norm n. Okay, norm n. Good. And casuale. Okay, okay, correct. 0, 1. I explain you in a moment what I'm doing. The important thing now is that I succeed. Inv norm n. Yeah, casuale. Okay, good. So what I did is to generate an outcome from the normal distribution or Gaussian distribution. I'm sure that you heard about it. It's a different distribution that is different from the uniform. The uniform distributes data between the given interval, 0, 1, in a uniform way. The normal distribution, you have to give an average and a standard deviation and concentrate the data around the average that you give and around how much around, depending on the standard deviation. If you give a small standard deviation, they are very concentrated around the mean. If you give a large standard deviation, they depart from the mean. And here I gave, look at the formula, it's mean 0, standard deviation 1. And let me explain. Inv norm n means that you compute, estimate a number that follows the normal distribution. But you have to give the probability associated to the number. So what is the probability that you want for this number? And then you have to give the average and the standard deviation. Why you have to give the probability? Because, of course, to generate a number from the normal distribution, you get different numbers for different probabilities. If you want a high probability, then it gives to you something close to the mean. If you want a low probability, and in this case is probability of not exceedance, if you want a low probability, then it departs from the normal distribution. And in order to give the probability, I generated a random number between 0 and 1 because I want to give a probability that is taken by chance, by pure chance. Okay? But you can make experiments here like, let me give a probability of not exceedance of 0.99. What number are you? Sorry, I need to put the comma here. You see the number is high. Now, let's put a probability of not exceedance of 0.01. The number is low, and normal distribution means that the numbers can be negative or positive. So you see that if you change the probability of not exceedance, if I put 0.5, I am around the average. I expect to be around 0. Okay? So, depending on the probability that you give, you generate these numbers that are concentrated around the mean. I just wanted to generating the different distribution to give you a different flavor. Now let me put again casuale because I want a random number. Okay, casuale here, and here I have a number that is generated by random. Okay, and this is my generation from the normal distribution. You see that there are some numbers that are larger, some numbers that are smaller. If I compute the mean of these numbers, I expect something around 0. Okay, you see, and if I make different generations, you see that I am always more or less close to 0. Of course, not very close because only 15 numbers. So there is some what is called in statistics sample variability, but you see. And so let's take a generation, let's fix it, okay? Like this one, I copy it, sorry. I copy it, and then I paste it. Okay, now I fixed the generation, and I want to compute the probability density for these values, 0, 0.1, plus 0.1, 0.2, 3, 4, 5, 6, 7, 8, 9, 1. I want to compute the probability density for these values, and I take a step of 0.1. Okay, so first of all, I have to compute the numbers here that are in each interval, and the interval corresponding to 0, if I take a delta x equal to 0.1, the interval is minus 0.1, and the second is, sorry, again, the comma, and the second is 0, is 0.1. This is the interval, sorry, again. This is the interval. For 0, I have to go back 1 delta x and let me think about it, because here the range is not from 0 to 1. So in the Blackboard, I refer to a range from 0 to 1. Here the range is different. So let's compute the range. Not I need to include negative values. So let me do like this. What is the max here? The max is 120 and the minimum, okay. So let's start from minus 1.5 and let's go step of 0.2, minus 1.3, minus 1.1, minus 0.9, etc. And then I can move forward plus 0.2, and let me move forward up to 1.5. This is the range that I wanted to compute. And is it clear why I needed to change? Because the normal distribution includes negative values. If I want to draw the graph, I need to include the full range. And then for each value, I take a step of a delta x of minus of 0.2. So here is minus 1.7 to 1 minus 1.3. And I want to compute the number of data that are inside this range. So let me put the data in ascending order in order to make it easier, okay? Otherwise, I make mistakes. Okay, so here there is one number, only minus 1.36, only one. Now, between for minus 1.3, we have to count Let me check. Here, I mean, the range, I need to correct the range, is minus 1.6, minus 1.4. Because otherwise the range overlap. They don't have to overlap, okay? So here I have at this stage 0. Minus 1.3, the range is from minus 1.4 to minus 1.2. So I have two numbers, two numbers, okay? I don't write the range here because it becomes, I can write the range actually, but okay, let me just go without writing the range explicitly, but I can do like this. For 1.3, we are from minus 1.4 to minus 1.2. And we have two numbers, okay? I have these two. Okay, next range, and let me avoid to write the range now. Let me, minus 1.1, I have to go from minus 1.2 to minus 1. So, two numbers. Two numbers. Three, let me, yeah, you are right, is 3, because there is also this one, 3. 3. Okay, minus 0.9, I have to go from minus 1 to minus 0.8. So it's this one, just one, I think. Then at the end of the story, I will make a sum and verify that the count is correct. Minus 0.7, from minus 0.8 to, I think it is 0. 0. Minus 0.5, from minus 0.6 to minus 0.4, just one. Okay. From minus 0.4 to minus 0.2, 1. And then here I have from minus 0.2 to 0. So it's 1. Here I have from 0 to minus 0.2. So it's 2, correct? No, it's 3, 4. 4.
0 to 0.2.
To 0.2, correct. From 0 to 0.2. So it's 4. Correct? Because it's from 0, it's 4. And now we have from minus 0.2 to, from 0.2 to 0.4 is 1. And then it's from 0.4 to 0.6, 0. And then I think it's 0 up to 0.6, 0.8 is 0. Yes. 0.81 is 0. 1.2 is 0, and then we have 1 here and 0 here, correct? Let's see the sum. Should be 15. 15, correct. Good, so we made the count. Now let's compute the frequency, plus this number divided by 15. This is the frequency. Good. And now let's divide by 0.2. Okay, so this number divided by 0.2, which is the interval. Good, and now we are ready to make the graph. Okay, let's make the graph. And the graph is, let me take this one, column, and I paste it here, values. Oops, sorry. Paste values. And now I can select and make the graph, okay? So insert graph. So this one is, I think we can take, let's take the dispersion, and let me take the points. Okay, this is my probability computed according to what I see on the blackboard. And here, the integral of these numbers, if I make a sum here, sum, what are you expecting? It's or it's not really correct that I ask you what are you expecting now. If I multiply, if I compute the integral of these numbers, the integral of this graph, I have the integral is the area. So in order to find the area, it's not just enough that I compute the summation. I also have to multiply by 0.2. Now I'm expecting 1. If I don't get 1, it's a mistake. 1. Okay. So I think that operationally you understood what I did. The graph is not very meaningful. Why it's not very meaningful? I mean, there is some meaning there. You see that the data are not equally distributed. The probability is not equally distributed. It's concentrated around the average, but it's concentrated in a way that is not very convincing. And the reason is that, there is only 15 numbers that were generated. It could be interesting to see if I make a longer generation, but actually to make it in Excel and to count the number of points in each interval takes time. When we will work with R and Python, I will show you that if you generate precisely something like 1 million data, you get a clear concentration of points around the average. But what I want to draw your attention on is I applied this formula and I divided by the length of the interval to compute the probability. And when I sum the probability and I multiply by the time step that I have chosen, basically what I do is to compute an integral of this graph. I am summing the probability that I have computed in this way. And the integral of this graph, if you think the way we have drawn it, must be 1. Because what we did is to divide the frequency, the sum of the frequencies, and the frequency is computed here. The frequency is, I counted the number of points in each interval divided by the total number of the points. So the frequency must sum 1. And for sure, if I take here the sum, it's 1, because the sum of the numbers is 15. The sum of the numbers is 15. Here I just divided by 15, so clearly must be 1. And here, what I did is to divide this sum that goes up to 1 by 0.2. So when here I multiply back for 0.2, I get 1 again. Okay, so this is the way we use to define the probability for a continuous variable. And keep in mind that what I can do now is to compute with these estimated probabilities, the probability of not exceedance. And to compute it, I take the sum of the individual probability, and the sum goes up to 1, because I computed there the sum is 1, like I was expecting. So the probability of not exceedance of the larger number of this one is 1. Which is what I was expecting. If I take these numbers that I generated, what is the probability of not exceedance of the last one, which is the larger? Must be 1. And therefore, this is why I said I am expecting that if I take the integral, if I take the summation of the probabilities, what I'm doing is, remember tossing the dice. If I take the summation of each individual probability, I compute the cumulative probability, which is the probability of not exceedance. And I get the same result here. The same result here, I am computing the integral, and what I'm getting is the probability of not exceedance. Okay, the summation is an integral. Okay, why we call the integral integral and not summation? Because the summation, you are working with numbers. When you talk about an integral, you are working on a function. Okay, and but what I did here is to take the summation, which is an approximation of the integral. Because now, if I made a larger generation, what is the shape that I would get instead of this one that is not very clear? The shape that I would get is go to Google, normal distribution, Wikipedia, here. Must be the normal distribution because just 1 second. Must be the normal distribution because in Excel I generated with the normal distribution. And this is a graph of, forget about the symbols. On the horizontal axis, you have the random variable x. In the vertical axis, you have the probability. Okay. And what you see is 3 different probabilities, graph of probabilities for different values of the mean and the standard deviation on the right. And you see, for instance, that the difference between the red curve and the yellow curve, they have the same mean. You see, the peak of the probability is on 0. But the yellow one has a larger standard deviation, so it's more spread. Okay. And the green one has a different mean, different average. Average mean, they are synonyms. Okay. So this is the graph that I would get if in Excel I made a generation of like 1,000, 1 million. I will show you in R because in Excel working with the large numbers is complicated. And also you have to make a manual count. But I really would like that you focus on what I did in Excel because it may look something that, I mean, try to repeat it. And if you make it, you really understand how the probability for a continuous random variable can be estimated. And another story is then to describe the probabilities with an analytical relationship. And you understand that here it is very useful because if, look at the screen, if I was able to describe this point with an analytical distribution, first of all, I may get an interpretation like these points are well approximated by what? I try with the Gaussian normal distribution, the normal distribution, Gaussian distribution, they are synonyms, okay? And I can try with a Gaussian distribution and I see that indeed there is a good interpolation. So the knowledge of the theory, the knowledge of possible analytical interpolation helps me to recognize the probability of the data and helps me in making interpolation, extrapolation. So it is important, after I estimate with the data the probabilities, to fit these probabilities with analytical relationship. The Gaussian distribution, let me, first of all, keep in mind that when you talk about continuous variables, usually what I called so far probability is called probability density. And you understand why, okay? You understand why. Because it's a density, the way in which it is computed, it's a density, okay?
Also, density in terms of point.
It is also density in terms of points in the graph, yes. But usually we don't use probability density for integer random variables. For integers, we say probability or cumulative probability. When you have a continuous variable, usually people say probability density and cumulative probability. But again, keep in mind that in the literature, they may use different terms. sometimes there are textbooks or papers saying just probability, and you don't know if it is a density or if it is a cumulative. And because there are some textbooks, usually they say it at the beginning, like, I call probability the cumulative probability, or I call probability the probability density. And then they also use the term probability function. Probability function means the analytical relationship that I use to interpolate the points. Second thing, remember, it's already implicit in what I said. Let's talk about probability and cumulative probability. For a continuous variable, the probability is the derivative of the cumulative probability, and the cumulative probability is the integral of the probability. Because look at the way I computed it. It's clear that it's a derivative, because I computed the difference and divided by the interval. So what we say is that, I use the same symbol here, capital P of x is the derivative of lowercase p x with respect to x. Okay, so keep it in mind. This means, as I already pointed out, that knowing the probability or the cumulative probability is dual. If you know the probability, you know the cumulative probability. If you know the probability density, you know the cumulative probability. If you know the cumulative probability, you compute the derivative, and you know the probability density for a continuous variable. And for the integer, you cannot say it's a derivative because it's not continuous. Okay, so the normal distribution, why? You have seen that I called into play first the uniform distribution because it's very easy. I give a range and the probability is spread in the same way. And then I called into play this Gaussian distribution. Why? The Gaussian distribution is very interesting because it has some features. First of all, it is symmetric. You understand what it means? It means that if you take this graph and you cut it around the average and you fold it, it's symmetric. Okay? Well, first, it's symmetric. Second, it is nice because the values are spread around the mean, and it is usually spread within a limited distance by the mean. Okay, you may increase the standard deviation, but actually you are unlikely, very unlikely, to get values that are exceptional. So look at the yellow graph. It is, very spread, but you don't see anything of exceptional here, because you expect some values departing from the mean. If you look at the data, even a small amount, you already see that, they are not concentrated around the mean, they are quite spread. It doesn't happen that you get data concentrated around the mean and suddenly an extreme, a super extreme. The normal distribution is not like that. By the way, this is what is concerning engineers, the super extreme. Like you observe earthquakes for a long time, everything is okay around certain values, and then puff, a super extreme. This is a problem. Because usually we look at historical data and make our design of the historical data. If a super extreme occurs, it's a problem. But this is ruled out by the Gaussian distribution. So it's nice. Another nice property of the Gaussian distribution, this is really, you may get observation of whatever random variable. Can be number of potatoes produced each year by a farm, can be number of tomatoes, can be river flow, can be whatever, okay? And let's suppose that these numbers are observed depending on time. And then you compute the average, like the number of tomatoes in 10 years, the river flow average over 10 years, and then the number of tomatoes in 100 years. You increase the average, the time span over which you compute the average. It can be analytically proved that for increasing this average window, every random variable, whatever it is, converges to this. And this is something that, I mean, is also understandable for an engineer, because, I mean, if you average out over a longer sample size, the effect of individual extremes becomes much smaller. And therefore, because it's smoothed out by the normal values, and therefore it's quite understandable that you get with your averages closer to the mean. So it's also understandable, but it's a very nice feature because it means that this is a kind of general rule. What is the limitation of the Gaussian distribution? There is one important limitation and one technical limitation. One important limitation is that our variables don't follow the Gaussian distribution. In environmental sciences, and usually they don't follow the Gaussian distribution, unless you take the average over a longer time span. But usually we work on like daily values or monthly values. We don't have enough data to compute the average over 100 years. So the Gaussian distribution is not very useful for us. And also the Gaussian distribution, I mean, being symmetric can assume negative values, and many of our variables are positive. And our variables are not symmetric. And therefore, you know, it's not very handy. Second thing, second limitation, look at the analytical expression. We look for an analytical, I said, expression, because we want it is this one. First, it's not easy to remember, but this is not a problem. You don't have to remember it. And this is for the probability density. Unfortunately, it cannot be integrated, so you cannot get a explicit representation for the cumulative. And this is quite a limitation for an engineer, because you have to integrate numerically. Okay, you may say, I can solve it technically, because I have numerical integration. It's very easy to integrate it, but still, it's a bit of a limitation. Now, let me show you, because there are hundreds of distributions. Another one that could be like a bit concerning, okay? Let me take let me see if I can gamble distribution. Gamble distribution. I hope there is, yeah, there is the Gamble distribution here. Okay, so this is the probability density of the Gamble distribution. What's the difference? Okay, you see negative values also here. It's not symmetric. Look at the right tail. The right tail describes the probability of extremes. It's longer. It's longer. So the right tail is longer than the left tail. It's longer. Okay. It has a good feature, the Gamble distribution. It's very easy. You can write the probability density function, it's this one, and the cumulative one in an explicit way. In this case, it's even easier to remember the cumulative than the probability. Okay. Here you don't see the left-hand side, okay? You see only the right-hand side. Okay, let me show you another distribution. Let's look for long tail distribution. Heavy tail distribution. This is also long tail, but let's look at heavy tailed. Let me see. I really would like a better graph. I don't like. Okay, let's see. Let me see. You see the graph here, log normal. I'm looking for one with a very long tail. This one, the V distribution. The Burr distribution, yeah, also this one is quite long, log logistic. Okay, let's take the Levy. So look at these tails, very long. And this is only for positive values, the Levy. So you understand that as an engineer, if your data follow these distributions, you are quite concerned, because it means that a quite large probability is given to values that are very far from the mean. The mean here is something like 0.5, maybe less than that. You see that you still have, look at the red line. The mean is around 0.5. And you have a very large probability of getting values that are 6 times the mean. So you are a bit concerned, because this means that it can happen something really surprising. So you see how the probability computed in this very simple way allows us to estimate, to understand what is the likelihood of being surprised by something. Typically, earthquakes are described by long tail distribution, but also some, it depends on the geographical region. Some probabilities for floods are described by a long tail, especially for small basins. I mean, you take the Po River, it's unlikely that you get, when you get a flood, it's like 5-6 times the average. If you go to a small river, the average is close to 0, and the flood is like 300 times the average. Okay. Now, of course, these distributions have their analytical relationship. Some of them can be integrated, others not. All of them depend on parameters. What are the parameters? In the Gaussian distribution are the mean and the standard deviation. In the uniform distribution is the range, minimum, maximum. And these other distributions have other parameters. These are constant that are plugged into the analytical relationship to fit the data. Okay, now it's clear that we are concerned by the right tail. Sometimes for some variables, we are concerned by the minimum, which means left tail. And for instance, for droughts, we are concerned by low water and not high water. But let's now concentrate on the right extreme. And let me go back to the slides of the American Society of Civil Engineers, because my recording of statistics and probability stops here. What I really would like is to make sure that you understood. So next week, just if you have questions, please, let's discuss. We will make other exercises in the lab by generating more numbers, and you will learn some more about this. But meanwhile, think about it, because it's really important that you understand probability, not only learning the definition. You have to understand technically what it means. You have to get the concept. And so I'm really motivated to make sure that you grasp the concept. Now, let me go back to the slides of American Society of Civil Engineers, because now we can understand the slide where I stopped here. Let me go here. You see, now you understand this graph. This is a probability density. It's not well presented because you don't see anything in the axis. They don't have titles. And then they say climate extremes. So they are concerned by the right tail. And therefore, in a way, and I come back to your comment, we have to estimate in the future climate this kind of probability distribution. Okay. In the present climate, we estimate it by looking at the data, like I did in Excel. But in the future climate, we have to use, I already mentioned climate models, and we will see how they work. Okay, here they say how climate change affects the likelihood of extremes, and this starts to give an answer to your question. You see here increasing mean, and they show the previous climate picture and the new climate. Just 1 second. Okay, and the new climate. You see, it is if the new climate causes an increase of the mean, it is shifted on the right. And this is referred to temperature. So you see that here they see more hot weather because there is some probability assigned to temperature that are higher than in the previous climate. Here there is an increase in variance because we don't know how it is changing in principle at this stage. It may be a change in the mean, it can be a change in the variance is the standard deviation to the power of 2. And I assume that you know what is a standard deviation and a variance, but if there are some doubts on that, just let me know. Another important statistic is the skewness. If you don't know, or asymmetry. If you don't know what is, just go to Wikipedia, look for skewness. It describes the length of the right tail. Okay, and here you have an increase in mean and variance. It may happen. It may happen, and then you get a shift on the right, and you see the distribution is fatter. We use the term, in statistics, they use the term fat distribution, meaning that you have a huge standard deviation. Thin distribution is standard deviation reduced. And they also say a fat right tail means that there is a lot of probability in the right tail. Okay.
So this is you also took the fact that the return period, so the average of the
yes
increases, of course.
Yes, because we have not or yet demonstrated that the return period is the inverse of the probability of exceedance. We will say that. But in a way, the return period is related to the probability distribution. And if you have an increase of the right tail, you have a decrease of the return period of a given extreme. But we will, this is something that I didn't say yet, okay? Now, here, they give another interesting information. In the United States, they present here the percentage change in very heavy precipitation from 1958 to 2011. This is interesting. I think they define here what is very heavy precipitation. They say defined as the heaviest 1% of all daily events. So the heaviest 1% means a return period of about 100 years, which is a standard reference in civil engineering. So the return period of 100 years, which corresponds to the heaviest 1% of the data, basically, these are the changes observed in the United States. And these are changes estimated in 2011. They are coherent with our current knowledge. 15 years already passed, but indeed they are quite usually to give a very rough indication. If somebody asks me what has been the recorded increase of daily precipitation with a retinal period of 100 years, I say from 10 to 40% in very extreme cases. Here there is a 74 that is unlikely, in my opinion, but all the other numbers, it's fine. Okay, daily precipitation. Hourly precipitation may be something more. But we will, I will give you a map of Italy with these numbers, estimated just in a paper just published, not by me, but by distinguished colleagues. They produced a map of Italy because it's important that you get an order of magnitude for rainfall, but not only rainfall, wind, etc. Okay, let's stop here. And do you have any question? Tomorrow there is, for those of you who are attending the lab, bring your PC like last time. Are you attending here? Yeah, okay, very good. Thank you. Okay, and let me just check if, yeah.
So also in Brazil, should we have to join the lab?
It's not, I mean, you took as an elective, I think, only this course, climate modeling, so you didn't take the lab, so don't join. Okay. You are missing something, but it's just, it's actually quite different because we talk about numerical computation, climate models. I mean, I don't think you shouldn't attend. Okay. Okay, thank you, Radha. See you next time.
Thank you, Professor.
Bye-bye.